In the last video, we ended up with the question, how many shells? How can we tell how many shells of electrons an element has? This is a question that got asked all the time at GCSE. And hopefully you came up with the correct answer, and that is to look on the periodic table. Just draw one quickly. There you go, look on the periodic table. And in GCSE, we looked at the periods. The periods told us how many shells of electrons an element had. And seeing as we know that the shells are actually just energy levels, now we can look at the periods to tell us how many energy levels something has. And from this, we can work out how many sublevels are in each energy level. So, if we look at our first two elements, hydrogen and helium, these are in the first period. That means they have one energy level. And seeing as hydrogen only has one electron and helium only has two electrons, and we know that the S sublevel only has two electrons in it, we can conclude that the first energy level only has an s orbital. Now if we look at the second one, we can see the first two elements, sodium and lithium, no, lithium and beryllium, sorry, sodium's down here, lithium and beryllium, these have the first two electrons of the second energy level. So the second energy level also has to have an S energy level. But along the period, we get into these elements here, like the carbon and the nitrogen and oxygen and fluorine. These elements are outside of the S orbital. There are 6 elements here. There are 6 extra electrons. Which sublevel has 6 electrons? The p. So the second has to have a p orbital as well. And we can continue doing this. You can do it yourself and see that the first 4 sublevels have to have these sublevels in them. So we can how do these elements fill up? How do these orbitals fill up? If we can work out how many of these orbitals each element has, surely we can write a way for it. We can find a way for each element to be written in terms of its electrons. And to do that, we need to know the rules of how these orbitals fill up. And there are 2 of them. The first one is the Aufbau principle, and this was developed by Niels Bohr, and it basically means the building up principle. And it's quite an obvious principle. We know that each energy level, this is the first, the second, that's an S, not a 2. Okay, the third energy level and the fourth energy level are increasing in energy. We worked that out with the diagram of the fat runner. But we also know that in each of these energy levels, there are the sub-energy levels, the SP, D, and F. This one only has 1, but so maybe that's a bad example to use. Let's look at the 4th energy level. In the 4th energy level, we have our S, our D, no, our SRP, our D, and our F. And these are also increasing in energy levels. D and F. Can't write today, sorry. So we know that all of these are increasing in energy levels, so we have a steady increase in energy. And the Aufbau principle, the building up principle, means that electrons fill the energy levels in increasing energy. So they can't immediately start filling the 4th energy level. They have to have filled the 1st, 2nd, 3rd energy levels first. And likewise, they can't start filling the d orbital first. They have to fill the s orbital first. So knowing that, we can start developing a way to write the electron configurations. But we also need another rule, and this is called Hund's rule. And this basically refers to the spins of electrons. If we can remember back, we know that each electron has spin. and it can either be spin up or spin down. I'll denote them with these arrows from now on. So we learned that in the previous video that electrons that occupy the same orbital have to have these opposite spins. But what I didn't mention was that the electrons like to be on their own first of all. Instead of pairing up at every chance, they prefer to be on their own. So Hund's rule describes this by saying that they occupy orbitals as single unpaired electrons with the same spin, and they only begin to pair up when there are no more empty orbitals. So if we look at the p orbital, we know that this has the p sublevel, we know that has 3 p orbitals in it. If we introduce one electron, it will do this. We'll only have one upspin. Then, when we introduce a second electron, it is not going to pair with the first one. It is instead going to be another upspin in the second p orbital. And likewise, if we introduce a third, it will go into the third one. Only then will they start filling up with the opposite spin. So that is Hund's rule. So knowing these two things, that they build up and that they don't pair immediately, we can begin writing these elements as electron configurations. But first, a little bit of notation. An electron configuration is written in 3 stages. First of all, we have a big number, and then a letter, and then a little number. This is a superscript number. What does this mean? Well, this first number is the energy level. This means that it's in the first energy level. This letter is obviously the orbital. Orbital, spelled it wrong. And then this superscript letter is how many electrons are in it. So we can write, for example, if we wanted to describe the state of the second energy level's p orbital, we could say 2p, if it had 2 electrons in it, it'd be 2p2. If it had 3 electrons in it, it'd be 2p3, and so on and so forth. So we can begin to build up each element using these electron configurations, and I have handily prepared this earlier. So we have the columns for the elements, the electron configurations that we will develop, and then we can draw the spins. So let's start with the most basic one, hydrogen. Hydrogen only has 1 electron. We know via Aufbauer's principle that it will fill up the lowest energy first. So it will begin to fill up the 1s orbital, and seeing as there is only 1 electron, it is 1s1. And we can draw this with a up arrow in the first s orbital. Then we look at helium. Helium begins to fill up the lowest one, but it has 2 electrons. So these pair up with opposite spins. And then let's go to lithium. Lithium already has a full s orbital from the 2 electrons that it has that are carried over from helium. Let's just pretend that we're adding electrons and protons to these so that we can see the build-up. So it already has a full 1s orbital. So it moves on to the next lowest energy level. And the next lowest energy level is the 2 energy level. And the lowest sub-level in the 2 energy level, if we remember back up here, when we drew out which energy levels have which orbitals in, this has an s and a p. So it will begin to fill up the 2s orbital, and it has 1 spare electron in there. So it begins with an up, a down, and then an up, and not a down, and 1 up in the 2s orbital. So then we can look at beryllium. I've started drawing this all wonky. Oh well. So it's got a full 1s orbital, and then we add another electron to the 2s orbital to make it 2s2. So we look at Hund's rule, they begin to pair up. And then we can fast forward a little bit to an element like carbon. Let's look at carbon. So carbon has its 1s orbital full, its 2s orbital full, but then it's got more electrons. So we look back up, we remember the 2 energy level has s's and p's in it. so it begins to fill the next lowest energy level, which is the 2p orbital. So it has an extra 2 electrons left over, so we put them in there. So we have 1 up, 1 down, 1 up, 1 down in the 1s and the 2s orbitals, but then with the 2p orbital we have 1 up, and it doesn't pair down because of Hund's rule. It fills the vacant orbital, and it continues on like that all the way down. And instead of writing out all of this every time, I mean, I have a horror story from my chemistry class where my chemistry teacher sat me down, all of us down, and made us write down the first, I think it was up to argon, no, I think it was even past argon, all the way down, writing out the full electron configurations and the full spin diagrams. It was horrible. So instead of doing this every single time, we can adopt a system where we can take an electron configuration of, let's say, a noble gas. The noble gases are the ones which have full orbitals. So helium is the noble gas, and it has a not full orbitals, full energy levels. So helium has a full 1 energy level. So if we say helium like this in square brackets, we know that everything that comes after this already has the electron configuration of helium before it. So it already has a 1s2. Now this isn't very useful with something like helium because 1s2 isn't that hard to write. But if we look down at something like, let's say argon. Argon has the electron configuration of 1s2, 2s2, 2p6, 3s2, and then 3p6. It goes on and on and on. So instead of writing this out every time, we can equate this to argon. So everything that comes after it, we can write with AR before, and then carry on our electrical configuration from the 4s orbital. So that was an introduction to Aufbau's principle, Hund's rule, and writing out electron configurations. We're going to be looking at some of the exceptions to these rules and tackling the blocks on the periodic table. I mean, I mentioned up here when I drew out the periodic table that we can work out how many of these orbitals we have in the energy levels from this, and that's taken a bit further with the idea of blocks on the periodic table. So we'll cover all of that in the next few videos. So I will see you then.